There are a wide range of results that are pretty critical to doing statistics broadly and inferential statistics more specifically. Among all of these results, however, none plays quite as key of a role as the central limit theorem. So the name would suggest that the central limit theorem is quite central to what we do with statistics, and that would be the case. If I had to argue the most important result in all of inferential statistics is probably the central limit theorem. And the key idea with the central limit theorem is that we want to be able to say as much as we can about sampling distributions with saying as little as we need to about the population distributions. And that's really where the central limit theorem is going to come into play. It's going to sit at the heart of a lot of statistical inference and a lot of the theory that drives what we do with statistics to conduct much of the science that we're conducting on a day-to-day basis. So when the population distribution is not normal, the sampling distribution of the sample mean is not going to be exactly normal either. In order to have an exactly normal sampling distribution for our sample mean, we need the population to be normally distributed. And often, we're not going to be willing to assume that the population is normally distributed. And so the question remains, what do we do in that case? And that's where the central limit theorem is going to come into play. So we can think about what's actually going on with non-normal populations, and specifically with the sample mean for non-normal populations. If x1 to xn, if we have our sample and that sample is drawn from a normal distribution, then we know that x bar is also normally distributed, right? So if we have a normal sample or a sample from a normal population, then we have a normal sampling distribution. This is not going to hold if we don't have the normal distribution in the population. So if x1 through xn come from any other population distribution, then they're not normally distributed once we take the sample mean. Right? And so what are we doing in this situation? In order to know in order to conduct statistical inference, we need to know the sampling distribution, right? So it's not sort of enough for us to look past this point. If we want to say anything about the mean of a population, if we want to say anything about the parameters that we care about, that we're trying to do statistical inference on, then we need to know what the sampling distribution is, because the sampling distribution is the key to unlocking our ability to quantify uncertainty that we have. So we want to say something about a population parameter. However, we're limited in what we can say by the need for a sampling distribution. And if the population is not normally distributed, then it's not going to be an exactly normal sampling distribution. Moreover, it's almost always going to be the case that we don't have exactly normally distributed data, that our population's not normally distributed, and very often it's going to be the case that we're not willing to assume it's even close to normally distributed. We might have something that's very skewed, we might have something with multiple modes, right? We're going to have data that look very different from the normal distribution. And so we have this issue. We need a sampling distribution. It's not going to follow the result of being exactly normal, but most data that we observe are going to be in this position of requiring something else. The central limit theorem tells us what we can do in this situation. And the idea is that no matter what population distribution we have, no matter if it's normal or if it's heavy-tailed or if it's skewed or if it's multimodal, no matter what it looks like, if what we're thinking about is the sampling distribution of the sample mean, then as long as we take big enough samples, as long as the sample size is large enough, then the sampling distribution is going to be approximately normally distributed. Okay? So no matter what the population is doing, we can still get a normal sampling distribution or an approximate normal sampling distribution. We can make this slightly more formal. So our central limit theorem, which is often referred to simply as the CLT, states that if n is large enough, and we'll touch on what large enough means a little ways from now, then no matter what the population distribution of x1 through xn is, x bar is going to be approximately normally distributed with a mean of mu, same as the population, and a variance of sigma squared over n, where sigma squared is the population variance. So again, this is going to apply to any population distribution that we can look at. By way of notation here, this tilde with a dot above it, this just means approximately distributed. So when we say that x bar is approximately normally distributed, we can write it in this way. Okay. The CLT as I was stating at the beginning of the lecture, is probably the single most important result in inferential statistics. And the reason that it's so important is because it allows us to take any population that we might care about, and as long as we have enough data points observed from that population, we can say something about the sampling distribution of the sample mean. And more often than not, we care about sample means, right? We want to know the means of populations. And so this is going to apply in a very wide range of scenarios, and it's going to allow us to start quantifying the uncertainty that we would like to quantify. So as long as that is large enough, the population distribution is irrelevant. We don't need to know anything about that as long as we're taking enough observations from it, right? And so this is what we were saying, where we want to be able to say as much as we can, assuming as little as we need to about the population. Once we have this result, we can conduct statistical inference, we can quantify our uncertainty, we can make probability statements about the sample mean. They're not going to hold exactly, but they're going to be close enough that's going to permit us to actually make meaningful conclusions from these results here. So sort of the key question that we need to answer then is, how large is large enough? Because this whole result relies on this idea that we're taking a large enough sample from the population. And so what does large enough mean? And this right here is sort of the hidden benefit to the central limit theorem. We actually don't need that many data points. So if you look out at textbooks, you're often going to see n equals 30 as the limit. As long as you're taking a sample size that is 30 or larger, then that's going to be good enough in order for us to use the central limit theorem. Now, I will caution against using n equals 30 as sort of a hard and fast rule. Sometimes n equals 30 is going to be perfectly the right amount. Sometimes you're going to need fewer than 30. Sometimes you might need a lot more than 30. But we're always thinking about numbers that are close to 30, right? Maybe it's 30, maybe it's 15, maybe it's 100. What we're not talking about is needing 1,000,000 data points, right? As soon as you're sort of into the range of 100 data points, you're for sure into a place that things are going to start looking approximately normal, right? And so it's not a hard and fast rule, but it is often going to be a fairly small number, and in particular, a very attainable number, right? So if we think about what we're saying here, as long as you can observe 30 data points, then you can treat things as being approximately normally distributed in terms of the sampling distribution of the sample mean, right? So as long as you have at least 30 data points in your study, as long as you observe at least 30 data points in the lab work you're doing, as long as you interview at least 30 individuals, then things are going to start to behave in a way that is predictable, that we can actually specify distributions for. The key result, or the key quantity that matters in terms of how many data points we need, is going to depend on how close to a normally distributed population we're starting with. If we have a very close to normal distribution, then we might be able to get away with far fewer than 30. If things are very far from normal, then we might need more than 30. But we'll take a look at that by way of example over the next coming slides. So in these slides, what we have going on here is on the left-hand side, we have a depiction of the population distribution. So in this first case here, we have an approximately normally distributed population distribution. And then on the right-hand side, we have 4 histograms that are showing the sampling distribution for various sample sizes. Okay, and so each one of these is going to be formed by taking samples of the given size out of the population. So in this first case, we're taking samples of size 10 from our population. We take the sample mean, and then we do this over and over and over and over again until we form the histogram that we have here. Right, we can do the same thing with n equals 30, n equals 50, and n equals 100 to form these 4 plots. And so there's sort of going to be a couple of different points that we can pull out here. The first is that we should see that as n is increasing, the population distribution becomes less and less relevant to how normal these plots are going to look. Okay, and so we should see that by the time you're getting n equals 30, n equals 50, n equals 100, even if we have a very non-normal looking distribution as the population distribution, this is going to start looking quite normal on our sampling distribution. The other piece to note is that we're going to have a reduction in variability, right? So if we think about the parameters that we're using in the central limit theorem, the mean should always remain about the mean, right? So 0 on all of these plots here. But what we should see is that the variability in the data is going to decrease. And you can see this by just looking at the range of data that we're dealing with, right? So here, negative 2.5 to 2.5, negative 1 to 1, 0.4 to 0.4, 0.3, 0.3, 0.25 to 0.25, right? So we have this shrinking variability. And both of these results are going to be seen throughout everything. And so in this first case, right, we have an approximate normal distribution. Everything looks normal, even at a size of 10, right? In this case, if you have a sample of size 10, that's good enough for us in terms of looking at things being approximately normally distributed, right? But that's because we're starting from a normal distribution. If this is exactly a normal distribution, then everything is exactly a normal distribution. So we can take a look at what happens if we don't start with a normal distribution. So the first example that we have going on here is what we call a heavy tail distribution. And so in particular, what we're thinking about is that this distribution is shaped less like a bell curve and more sort of coming out aggressively in these tails here, right? And so if we have, thinking about what's going on, we have a lot more data that are hanging out sort of in these far extremes. And we can even see that just in terms of the, it goes from -10 to +10, right? And so we have sort of this extreme tail distribution here. And so what are we going to expect to see? Well, other than the extreme tails, we have a fairly normal looking shape, right? It's symmetric, it's centered on 0, sort of is behaved quite similarly to our normal distribution. And so even at a size of 10, it doesn't look so bad here. Now, what I'd point out is that this distribution still has a little bit of this heavy tail going on, right? It's still a little bit going like this. Whereas as soon as we're up to a size of 30, then we have that sort of standard bell curve shape that we're used to seeing here, okay? And so the idea is that here, we probably need a few more samples to get to something that looks normal, but somewhere between 10 and 20 is gonna work out perfectly fine between 10 and 30, because by the time we're at n equals 30, we definitely have enough samples. So maybe something like n equals 20 would be good enough here. As we go up to larger and larger sample sizes, we maintain our bell curve shape here, and our variability is reducing, right? And so in this case, with our heavy tails, we need more samples, but still not so many. We can look at an example here that's a lot less normally distributed, right? So we have this major positive skew in our population distribution, right? And so with the population looking very non-normal, we can ask, well, what happens with our sampling distribution, right? So again, we're looking at our sampling distributions over here. And at a sample size of 10, you can see that we still have this sort of positive skewness going on. And same thing with a sample of size 30, right? It's a lot reduced from where it started, but we still have a positive skewness. And so this is where I would start to caution that n equals 30 is not always going to be a perfect cutoff point here, right? If we go up to n equals 50, at n equals 50, we're probably mostly gotten rid of that skewness here. And by n equals 100, we've definitely gotten rid of that skewness, right? And so in this case, we probably need more than 30, but fewer than 100 data points. And again, if we think about what's happening here, right, we have this population. The population looks like this sort of extreme skewed distribution. This is the data where the data are always going to be coming from. But by sampling from that distribution and then taking the sample mean, the sampling distribution is going to end up looking normal as long as we get enough data points. So perhaps around n equals 50 in this case. Okay. This result here looks at, again, another distribution that starts very non-normal, right? It's a uniform distribution. And in the case of taking a small sample out of it, say at size 10, we don't have a very bad looking distribution here, but we probably have actually too light of tails, right? It doesn't sort of cut down quickly enough for it to be well normally distributed. But by the time that we're up to n equals 30, things are looking good here again, right? So here, population distribution is constant across the whole range, but the sampling distributions, because of the central limit theorem, are going to end up looking like bell curves. They're going to look normally distributed, and by the time we're at n equals 30, and then again, definitely at n equals 50 or n equals 100, we have those nice bell curve shapes that we're used to looking at, right? So we start from a very non-normal population, we get normal sampling distributions. The last example here deals with a multimodal distribution, right? And so this is non-normal. We have peaks in 3 different spots, right? It's sort of non-symmetric in a lot of ways. And so again, we can see that this population is behaving sort of erratically in many ways. But by the time that we're taking moderate size samples from it, so n equals 30 or n equals 50, say, then the sample mean has this nice normally distributed sampling distribution, okay? And so once again, our variability is going to be reducing over the entire range here, okay? And the mean is always going to be centered on the correct value of the actual mean. But as those sample size increase, then we are going to be seeing the distribution converge towards what appears to be a normal distribution for us. And that's owed to the central limit theorem. So how do we go about using the central limit theorem then? Well, if the population distribution cannot be assumed to be normal, then we can invoke the central limit theorem, right? If we have a normal population, then we don't need the central limit theorem. But if we have anything else, then we can invoke the central limit theorem. And the first thing that we have to do is verify that the sample size is large enough. So again, that n equals 30 cutoff is going to be oftentimes good enough, but that's not a hard and fast rule. Sometimes you might need a little bit more, sometimes you might need fewer, but as long as we have a large enough sample size, then we can say, okay, the central limit theorem is going to apply here. Once we know that, once we have a large enough sample, then we know that the sample mean has an approximately normally distributed sampling distribution, right? So the distribution of the sample mean is going to be approximately normally distributed. There's two important clarifications I want to make on this. So the first is that this does not mean that the population becomes normally distributed. Okay, the population distribution is whatever it is. We don't care what it is very much. It's the sampling distribution that we're thinking about. So if we think back to those visual examples there, that left-hand plot is not going to change. If you take a larger sample size out of it, you're not changing that left-hand plot. The population stays with whatever distribution it has, whether that's normal or exponential or multimodal or something else. The population distribution remains the population distribution. It's the sampling distribution that's changing. The second point, and it's related to the first point, is that our sample also doesn't change its distribution, right? If we're thinking about our frequency distribution, that's not going to change either, right? Our sample is still coming from whatever the population is, and so it's still going to reflect whatever the population is. However, the sampling distribution, when you combine our whole sample together into the sample mean, that is the quantity that has its distribution changing, right? And so it means that the sample mean itself is going to behave as though it's drawn from an approximately normal distribution, not that the sample is, and not that the population is. Okay, so it's important to clarify exactly what we're talking about here, but once that's all clarified, then we can actually use the normal distribution to compute probabilities or quantify uncertainty about the sample mean. So we can ask probability questions. What's the probability that the sample mean falls into a particular range? Or how uncertain are we about the value of the sample mean? All of that is going to be able to be done by using the normal distribution, and the use of the normal distribution is justified by the central limit theorem. Okay, and so to summarize what we're doing there, the central limit theorem is going to permit our doing of statistical inference for sample mean in almost any population, right? So we don't really care about what the population is. As long as we're taking a large enough sample from it, then we can use the central limit theorem to conduct statistical inference, to ask probability questions, and to quantify our uncertainty. And so we're able to make these statements about the distribution of the sample mean without needing to know very much about what's happening in the population.